Hi, and thanks for joining me for this presentation titled, Can You Hear Me Now? A cross comparison between traditional bird counts and audio recording systems for bird richness estimates. Before we start, why study birds? Well, birds can be used as an indicator of an ecosystem's health. Also because people like birds, you can use them as a symbol of a larger conservation or restoration project. In the last little while, there have been some new technologies that have emerged, and they have the potential to be used in bird monitoring projects. Can these new technologies replace or at least complement traditional bird monitoring methods? That's what I try to find out. A bit more about traditional methods. A widely used method in New Zealand are 5-minute bird counts. That's me on the right doing a 5-minute count. This involves someone going to a location, staying stationary for 5 minutes, and recording all of the birds they can see or hear. As a method, it is cheap, easy to run, and doesn't require specialized equipment. It does, however, require specialized staff. Some of the new technologies are what it's called automated recording units, ARUs. They are basically audio recorders, and they can be a custom-made device like the one on the top right, or a phone or a recorder with a microphone attached, like the one on the bottom here. The way these recorders are used are they are taken to a location, left on site for the duration of a study, and then they are collected at the end. Someone then goes through all of the audio recordings and identify birds based on their vocalizations, either their calls or their song. As a method, it's non-invasive, which means birds don't get disturbed by someone walking on the site. They can also be used in remote locations, particularly if they have solar panels attached to them. One of the downsides is the vast amount of data collected. These recorders may record all the time and generate hours and hours of audio files that have to be manually analyzed, and that's just a hard task. Where are we in terms of comparing both methods? As I said before, the recorders are a relatively new development. They've been used for the last 15 years. The graph here on the right shows all the papers that have been published that have the keyword ARU in them. The highest number is 14 in 2014. There was a handful of studies comparing both methods, manual counts and recorders, but there have only been 2 studies comparing specific models of recorders. And that's exactly what I tried to find out. How do these recorders compare to humans? And how do the recorders compare against each other? We did our study in a location called Poplar's Range. It's in northern Canterbury, 15 kilometers down from Lewis Pass. It's in an area of mixed beech forest, and there's also some Kanuka groves around it. In terms of bird species, we have exotics and natives, and also some endangered native birds, such as kakariki. For the experimental design, we use the same setup as previous studies, 20 sites spread across 4 tracking tunnel lines. We had 2 observers doing manual bird counts, a novice and an expert. And we also had 2 audio recorders, the Department of Conservation AR4, which is here on the left, the black one, and the 2040 bird monitor, here on the right, the green one. The Department of Conservation AR4 recorded for the whole time, 4.5 days, and the 2040 bird monitor recorded 32 times a day for 1 minute in length at random. To do the comparison between manual counts and the DOC recorder, we found the 5 minutes of the recordings that matched the manual counts based on the timestamps of the counts. We listened to the recordings and we identified all of the birds that were present. To compare the recorders against themselves, we did exactly the same. We found the recordings that match in time based on their timestamps, extracted them, and detected all of the birds present based on their bird noises, calls, and songs. And this was what we found out. Surprisingly, there was no significant difference between the mean number of species detected between the Novice, the Expert, and the DOC recorder. Here on the x-axis, we have who collected the data, the Novice, the Expert, or the audio recorder. On the y-axis, we have the mean number of species detected, and the arrow bars represent the standard error. Again, no difference. In terms of the total number of species detected, the species richness, there was a large overlap in the species detected, but each method detected unique species. Here in this graph, a row represents who collected the data, a column represents the bird species, and the colors indicate the identification certainty. So green means that we are certain that species was there, we saw it or we heard it quite close. Yellow means that we think that species was there, but we're not sure. So maybe we heard a faint call in the distance and we thought it was a falcon, but we couldn't be 100% sure. Gray means that that species wasn't detected at all by that method. For example, the Novice was the only one to detect green finches with confidence. The humans were the only ones to detect the New Zealand falcon. And we could only detect the presence of tui by listening to the recordings. What about machine versus machine, recorder against recorder? Well, here it was a different story. There was a significant difference in the mean number of species detected. What about the total number of species? What I found out was the DOC recorder detected 50% more species than the 2040 recorder. This seems to indicate that there is a difference. In total, the DOC recorder detected 19 species. The 2040 recorder detected 13. And if we only include species where identification was certain, we're down to 15 for the DOC recorder and 9 for the 2040 recorder. Some species were only detected at all by the DOC recorder, such as long-tailed cuckoo and the New Zealand falcon. We'd like to point out some limitations of our study. We did the manual counts in windy and rainy weather, so they should be repeated in different weather conditions. With the REUs, we had some data loss. This was probably because of human error. We didn't have one of the recorders with us for the field tests, and this highlights the importance of field testing the gear that you have. We also found out while we're listening to the recordings that the clocks of the both recorders didn't match, and even between themselves of the same make. Also, they drifted in time at different rates. So if possible, we recommend future studies to use syncing mechanisms such as GPS. To conclude, recordings, yes, they can be used to replace or at least complement traditional 5-minute bird counts, but they need to be tested before they are deployed so we can understand what's their performance and how much variance there is between models. What I think is really exciting about this new technology is the potential to be used in remote areas of New Zealand for bird monitoring. As you might know, there's a new effort to start a new New Zealand bird atlas. They are doing this with crowdsourced identifications, but some areas don't have enough data because they are in remote locations. Could we use these recorders to get that data and get a new bird atlas maybe every 5 years or maybe every year? How cool would that be? I'll leave you with that thought. I'd like to thank the many, many people that have helped me during this project. My Site 393 colleagues and staff, Myles Mackintosh, Tim Curran, John Sullivan, 2040 and the Lincoln University for providing the bird monitors, the Cacophony Project and the iNaturalist community. That was great at helping me identify bird calls that I wasn't aware of what they were. And I'd also like to thank Jonathan Hardy for automating many of the tedious tasks. To all, thank you. And to you, thanks for watching.